data modeling with objects. How many people here have ever done data modeling of any shape, form, or fashion? A couple. How many people here are sort of kind of familiar with data modeling? Okay. Okay, I had a bunch of slides at the beginning that I was trying to figure out how much time I should spend on them, and the answer is a lot. Okay, my name is Damien Gray. I worked here at NI for 15 years on a lot of stuff, and I left about 2 years ago. I am now an industrial physicist. I'm principal laser optical engineer at Stratasys, which is a 3D printing company. I'm deeply playing with FPGAs and RT systems. I'm doing motion control of 8 axes at 100 kilohertz, for example. Fun times. But anyway, and this little piece of software I'm about to show you was one of the things. I was calibrating it, and I needed some really weird functions, and I had to do some data modeling of it on the fly and make it fast. And so this is what happened. Okay, so I'm going to define what data modeling is. I'm going to give you an overview of what data modeling code is available in LabVIEW, and there is actually quite a bit. If you're not interested in speed, you probably don't need to do anything, or flexibility, I should say. So anyway, and then I'm going to show you my framework, and then what I did, and some quick examples on how it works, and things that could be done in the future. Okay, what is data modeling? Data modeling is you're trying to take a function of some sort, polynomial, sine wave, something, and you're trying to see if the data you have in front of you, the discrete points, are actually described by that function. Examples are fitting a line to a set of points. You can fit a sine wave to a periodic thing. You can find peaks on backgrounds. These examples actually get progressively harder as they go down. Fitting a line to a set of points is trivial. Fitting a peak on a background is surprisingly hard, but there is a VI in LabVIEW to do that. Finding an ellipse from a set of XY points is very difficult, and it's almost impossible to do with the current LabVIEW code because it is a bi-valued function. And it's nonlinear. So anyway, but my example shows you how you can do that. Okay, implicit in data modeling is there's kind of two things you need to worry about. There's linear problems and nonlinear problems. Linear problems are things that are linear combinations of basis functions. The classic example is just a simple polynomial fit. You've got a constant times x, you've got a constant times x squared. The same is also true, though, of Fourier transform. You've got a constant times some sort of sine function, you've got a constant times another sine function, etc. So those are simple linear functions. And those are typically not too hard to do, as I'll get in the next slide. The nonlinear functions are the weird ones where you've got Gaussian peaks or ellipses or sine waves or, I don't know, spherical harmonics. Anyway, and that's one class. The other one is the error distribution. When you're doing a fit, a data fit or a model of data, one of the things you always have to worry about is how is my error distributed around that function. So if you have a line and you just have random errors around it, typically you assume a Gaussian fit, a Gaussian error distribution, because that is the random error distribution. However, in a lot of industrial processes and even just calibration in general, that's not actually what happens because, for example, say you've got 20 points and someone is taking these 20 points by hand and typing them in and then running a line fit through it. Well, every once in a while, someone's going to flip two digits or get one wrong. And that's not a Gaussian error. That's something else. And it could be a fairly subtle error. Say you change a number from a 2 to a 3, but it would be enough to throw off, say, the intercept of a line quite a bit if it was in the wrong place in the line. So you can use a different error distribution that has longer tails to reduce the effect of something like that. And the standard Gaussian distribution, well, actually, let me go one more before I get to that. Okay, linear model with Gaussian distribution. This is actually a directly solvable problem. There is actually a fixed formula you can use, and it will just give you the answer. The techniques called least squares. Also, singular value decomposition is another way of singular value decomposition is a matrix technique for huge arrays of things, and especially if you've got huge long basis functions or something. And it works really, really well, and it's very fast. It also has one very good quality in that if you have something, your basis functions are assumed to be more or less orthogonal, so one of them does not overlap the other one. Sort of like a sine wave and then twice the sine wave. If you add the two together, you don't get they sort of don't overlap each other as far as frequency range go. So if you have basis functions and you're using SVD and the basis functions are not orthogonal, then SVD will just drop one of them to almost zero. And if you've got something, if you're running into round-off errors, SVD will drop the coefficients to zero because it just doesn't know what to do with them. So one of the problems with SVD is it's very easy to run into round-off errors, even with doubles. The second line down is nonlinear modeling using Gaussian techniques. So you've got you assume a Gaussian distribution, but you've got a nonlinear model like a sine wave, or say a Gaussian peak. There is a least squares technique called Levenberg-Marquardt, and it's in LabVIEW, and it will allow you to iteratively find a solution. Most iterative solutions require you to give it a starting point, and then the better ones actually will give you bounds as well. And if you look at there is a peak fit VI in LabVIEW that you can just say, okay, I've got this data, I want to fit a Gaussian peak to it, and it asks you for the original values, and then it gives you a boundary for each of those as to how far it can go before it'll just stop. Finally, and the really nasty stuff, if you have a nonlinear model or if you have a non-Gaussian distribution, then you have to solve it iteratively using a minimizer. Now, all data modeling is essentially trying to find a minimum. So what you've got is you've got this data model, you've got a set of data, and there is an error or an error of some sort between your data and the model at that point. And what you're trying to do is you're trying to change the parameters of the model so that the sum of the errors from all of the points is a minimum. And then you have achieved your fit. So essentially, you've got a minimizer, and then you've got an error function. Now, with the Gaussian, the error function is essentially the square of the distance between your model and your point. With a couple of the other ones, like the bi-square, I think it's called, or the double exponential, is essentially the absolute value. And finally, there's the Lorentzian, which is 1 plus the absolute value and the log of the whole thing. So it's an even longer tails. So depending on what you need to do, you can use any of those models. So let me, where's my, there it is. Okay, so modeling of mathematics. Let me grab an example here, and this is a simple line fit. So I've got 20 points. I'm going to start at 10. I'm going to increment by 10. I've got a slope of 10, an intercept of 10, and my error is set at about 40 points. Okay, and this is a random error. So I run it. You can see it does a nice, kind of distributes those along the points. If you look at the code itself, it's fairly simple. I just generate the points here. Then I use the canned off-the-shelf linear fit routine, which takes in x, y. I didn't worry about weight or tolerance, although you can. And I picked the normal least square method. See, it's also got least absolute residual and bi-square as well, so those are different distributions. And then parameter bounds if you want to put them in. And then it gives you, the nice thing about these things is they give you the actual data points of the model, so you can compare them, which I did here. I just plotted them all in together. If you go to the mathematics fitting, you'll see a plethora of fitting things. You can fit lines, which I did there. You can fit exponentials, powers, Gaussian. This is the one I mentioned earlier. Logarithms, polynomials, and then there are several other more advanced things. Here's the interesting one. You can fit on a sphere. I don't know how that made it in there, but it did. Somebody somewhere probably needed it for something.
Just because they knew at some point someone was going to give a speech and was going to say,
what the heck?
You can fit on a sphere.
But not in a ellipse. No, but it's a sphere. It's not a circle. It's a sphere. Now you can probably special case it to be a sphere, a circle, by just putting all one of the values on one thing. But don't ask me. Unfortunately, if you cut a sphere any way, it's always a circle. So on a plane. Anyway, so that's your basic. Let's see. Did they have? I'm trying to remember whether it was here or the other place. Yeah, I think it's. Yeah, I think it's this one. Is it this one? Methodly square. No. This one does give you, you can see it uses the SVD algorithm as one of your options. These are basically, when you're doing large linear fits that have an exact solution, you can, there are various ways of doing the matrix math, and this is basically gives you a bunch of different ways to do the matrix math. Use SVD. Use the default, unless you really need to otherwise. I'm trying to remember where it was. Probably in the other one. Mathematics, fitting. Nonlinear curve fit. That one's probably it. Okay, yes. This is the, let me pull this up. This is the one I referred to, the Levenberg-Marquardt fit. So this gives you X and Y and weights, but this one also has a set of initial parameters. And it has a function. So it has a VI reference that actually implements the function that you're fitting against. And this is a very powerful thing, because then you can do big, multi-dimensional fits and everything, and anything that you can feed into that function, you can, or anything you can do with this VI call, you can create a function for. So that's really nice. You can also, if you're into pain, you can use the, let's see, where is it here? Yes, you can use the formula string. So you can use your, the formula string is, I don't know if you guys have ever used the function parser. It's actually a fairly powerful technique, but it's kind of slow. It's amazingly fast for what it is, but it's kind of slow. Anyway, okay, so that's your the basic fitting stuff that's available in under the mathematics fitting palette. Now, if you want to get into weird stuff, like I'm about to, the place you want to go is mathematics into optimization. Let me in that. Come on, you. Optimization, there it is. It doesn't like me. Okay. Yay! Okay. Most of these, are deal with two-dimensional problems. There are a few exceptions. This one, the conjugate gradient, is basically a multi-dimensional minimizer. So it takes where it is, finds the gradient to the lowest point from that, and goes down it until it finds a minimum. It's very fast, but it's also easy to confuse it. The downhill simplex is slower but more reliable. It basically makes what's called a simplex. You can see the little triangles on the icon. It has a simplex is an array of points, one more than the number of variables you're trying to change, so your model parameters. And the simplex starts out, okay, this is what I want to start with, and then it varies each one of them just a little bit, so you have this circle or multi-dimensional thing of that gives you different error values around this area, and then the simplex kind of moves like an amoeba toward the low side. But it can go through. If you run through the mathematics in depth, it actually is a more robust way to find a minimum than the conjugate gradient. I'm sorry, that's a really poor explanation, but I would highly recommend, if you really want to know about fitting routines, and all the little minutiae and details, look online at numerical recipes in C. The full book is actually, the older book is actually online. And trust me, those algorithms have not changed since I first used them back in the early 90s. They're still good, they still work, and in fact, if you open one of these things and look at it, it exactly implements those algorithms right down to the labels on everything, which is hilarious. But since it's implemented in LabVIEW, there's no copyright issues. The big problem with these, though, OpenVI, is you notice how you enter your function on these. Yes, it's our friend the equation parser again. There is no way on these VIs to use a VI server call.
Well, and you can't actually code the algorithm if it's blocked by text.
Well, if you can code the algorithm in a function call, you can do it. But I've ran it like an ellipse, you can't because it's by valued and it doesn't work. But you also there are other things like if the function isn't available in the equation parsing functions, you're hosed. There's just not a whole lot you can do about it. So I needed to use a downhill simplex or a conjugate gradient or something similar in my code. I was running thousands of these per second trying to do a calibration for my high-speed motion control, and the equation parser wasn't going to cut it. So I went with an object-oriented approach that I could actually change the error functions trivially, and it's very simple. My top-level object is the minimizer, and it has all the things you would expect a minimizer to have. What kind of accuracy do you want? What error do you have what's the error value you got for the last run? One thing I did put into it was the error function itself is an actual class, and it is a class member of the minimizer. So the minimizer, when it runs, will call the error function to generate the error. So if you want to try several functions really rapidly, it's very easy to do so. You don't have to, you just derive from the root class, and you basically got one function to fill out, which is the error function. And then everything else is there for you. You don't have to do anything else. And the minimizer itself, I abstracted so that I've got I actually did two different things. I did the Nelder-Mead, which is the downhill simplex, and the conjugate gradient. I implemented both of those to try them both out. I basically just copied the LabVIEW code, cleaned it up a lot, removed a few ancient things. These things look like they were written in the 90s sometime. They probably were. And
as you just said, the math doesn't change.
Well, the math doesn't change, but they used a lot of weirdness that you used to have to do in LabVIEW that you don't anymore. And they also didn't pay attention to memory copies very well. And back in the 90s, we didn't have the tools to do that.
Right.
So anyway, I cleaned them up a bit and then added and basically replaced the function parser with my error function. And let's see what we get. Okay, so this is a fit for an ellipse. Now I've got it set up for a circle right now, so let's make it an ellipse. Okay, what this does is it generates a random angle and then calculates the ellipse point at that point, and it does this 10 times to give me 10 points, and then runs the fit on it and see how well I do. So there it is. There's the random points, and not too bad. Given the amount of error I threw on that thing, that's not too bad at all, actually. If I ran it often enough, every once in a while it would fail because the points would all be to one side or something. One of the things that is very important to do when you're doing iterative fitting is to get your initial conditions right. And so every problem is usually different. So with an ellipse, how do you figure out what the center is and what the major and minor axes are? The answer was that I you've got to get fairly close. So what I do in the code is I generate the ellipse, and then I do a simple set of code that figures out more or less, I assume it's a circle, because that ended up being more robust. When you had points all at one side or another, basically I looked at the difference in the maximum and minimum in both the x and y axes, took the maximum, divided by 2, and used that for the semi-major and semi-minor axes. And then the center is just the center of the max and min in both the x and y axes. And so that gives it the starting conditions. Okay, this is the error function. So you can see there's not much to it. I just define it. I give it the points, which I've generated here. I tell it what points it is. I tell it the error function. So let's see, that's the ellipse.
Sorry, what's the logic for your starting point again?
Oh, the logic for the starting point. I have just generated a group of points. I don't, and in theory, if you were actually doing this, you wouldn't know what they were. You wouldn't know what the original. So what I do is I take all of the points and I take the maximum and minimum in both x and y, and then I take whatever the average of the maximum and minimum gives me my center point in x and y. So that's the center of the ellipse, and the half of the distance in x and y, the larger of those two, whichever it is, gives me and I put that into both the semi-major and semi-minor axes. So for the ellipse, and that gets me close enough so that it'll converge. And you have to. That's the key with almost any iterative thing. You have to get close enough so it converges. And close enough really depends on the problem. The problem I was actually solving, which unfortunately I can't show you, was I had to get so close that when my starting conditions looked like they were good, but the fit actually found a better fit. So sometimes it takes as much time to figure out how to find your starting conditions as it does to actually run the fit, and that's very problem specific. It depends on how complex your function is. In this particular case, the ellipse is not a particularly complex function, so this works fairly well for it. Okay, let's go to.
So how many children do you have on the errors for? Or is that just, oh, I'm preparing in case I need another error?
Oh, well, I was about to show you that. Okay, here's the generic error function. It has almost nothing as far as parameters go. It has, and the parameters here are the values that you're giving it. In this case, actually no, I take that back. The parameters here are the parameters you're trying to fit for. So I'm trying to fit, slope and intercept of a line, or in this case, the semi-major, semi-minor, and center points. Those are my parameters. So that's the only thing that the generic error function has. It has a property called has derivatives, and this is basically a constant for the children, and that is used by the conjugate gradient because the conjugate gradient uses derivatives to figure out where it's going. And if the function has a function which calculates derivatives, it will use it. If it doesn't, it will numerically calculate the derivatives. And there's get the parameters. Okay, the calculate error is a pass-through because this has to be done by the actual function itself.
Virtual method.
Yeah, it's basically a virtual call. Close fit and initialize fit are basically things that run before or after the fit in case you have to do some sort of setup and tear down of your data structures. Most are not going to use them. You can override them if you have to, but if not, I mean, they're just blank functions. Okay, so that was the generic error function. Now let's go up here and do the ellipse Gaussian error. Okay, now I personally made the decision that the data points that you're trying to fit to are fed to the function and are fed to the specific function. And the reason I do that is because each specific function has different forms of what data points it wants. it would be just as valid to have several classes or several children of the generic error function, which had specific data point types, say a X and Y arrays, or an array of XY clusters, or an X, Y, and Z array, or some, whatever. You could do that just as easily. That was just a design decision I made. But other than having the points, the only other function here is calculate error, and it calculates the error. So it gets the points. These are the actual XY points. Then these are the parameters, and it runs through everything. This is getting the ellipse, and it should equal 1. So if it doesn't equal 1, then that's the error. So subtract that from 1. This is a Gaussian error. You see I'm squaring it here. I could have made that an absolute value, and it would have been a double exponential. I could have made it absolute value plus 1 log of, and that would have been Lorentzian. And each of them have their pluses and minuses. And I always try all three of those when I do any problem, because you never know which one's going to work best. Typically, for normal problems, the x squared here is usually good, because it gives you steeper slopes and faster convergence. If you use the simple absolute value, it's sort of a intermediate, and it's more immune to error and noise. And if you do the log of 1 plus the absolute value, then you're even more immune to noise, but it slows things down even more. So it really depends on what your problem is and what you're trying to solve. Anyway, but that's the ellipse. And so I set the ellipse, add the points. I set that as the error function. This is the downhill simplex. You can see my little triangles there. I do have to set the initial conditions, but the accuracy and the max iterations usually is good enough. I then run the fit. Oops. And what I do here, I'm going to talk about this one in a minute, but I call the initialize function. I call the the private minimizing function from the minimizer, and this is the top level parent minimizer. And then I call the teardown. I was thinking about this. I should probably have done this in a data value block to prevent race conditions here. But because I'm basically pulling something out of a cluster, using it, and pushing it back in a cluster. What? Yeah, someone's using it elsewhere. I could screw something up, but that really shouldn't happen anyway, because it's all, No, these are not singletons. Yeah. Anyway.
Old eyes. The green banner VIs, is that your error function?
Those are the error function ones. And
calling that within generic minimizer.
Yeah, this is the initialize error function, and this is the
close
error function.
Initialize is bracketed by. There's two VIs that bracket your initialize.
Oh, that's get the function and store the function. I have to get the function from the actual minimizer object, because the function is specific to it, and it's basically a value in the it's a data member of the.
Why are you using accessors there?
I don't have to.
Okay, because if you create the accessors, then you're making those available to the outside world.
Right.
And that's okay. But
I have to have this one, but I have to have the set so I can set it.
Well, because I'm thinking about your race condition, and I'm thinking about somebody coming along and doing those get and sets, and then performing your function on there. I wonder if you could use a protection proxy to
I could probably make this one the get private, because no one else should be getting that.
Yeah, or just eliminate it because you're in your own space.
Yes, I am in the own space, and I could use a data value block too.
Right, because if you're here, you can guarantee that you'll never have a race condition and not worry about your DVR.
Right.
The problem is if you're, it's like, and not having thought it through, the problem is other folks using those functions to do mischief outside of your class.
Yeah, it's unlikely though, because this is, it is a class and it's about by value thing. So nobody can get to this class unless they split the wire, and then it's not this class anymore. So this is probably okay.
But that's something that I've been playing with several months.
Yeah.
Using your class structures as a protective measure.
Of course, this probably makes a copy of this class coming out, and then so it offends my sense of efficiency to do this, but as Darren would tell you.
It probably doesn't make a copy.
Right here?
If it's just reading.
Yeah, it's just reading and then doing it and writing it back.
Probably not making a copy.
Oh.
Tyler's smarter than you.
I know it is. It's a lot smarter than it was back in 2000. That's for darn sure. Anyway.
And you can play games with swapping. There's a swap memory, so you can take something out, put a dummy in.
Yep, been there, done that. Anyway, the other thing you need to remember if you're doing any sort of iterative problem solving like this is after you finish, run it again. It's amazing how many times it actually makes a difference. Because a lot of times you can get hung up in a local minimum, but when you run it again, then you generate another. Now, if you're doing this with a conjugate gradient, it won't get you anywhere. But if you're doing it with the downhill simplex, when you start, you've got your start condition, which is presumably close to a minimum, and then it creates a ring of minor perturbations from that. And if one of them happens to be over a hill and there's another minimum over here someplace, you'll get there. And that happens more often than you would expect. Anyway, so it tries again, and then I grab the final values and plot them out.
Do you try again with use initial conditions?
I try again with the conditions that came out of the first fit.
Oh.
So he's using the first pass through as he makes a guess, which is completely uninformed except by mark one eyeball or what have you.
Yeah.
Then he calculates an answer based on that guess, and then he uses that as the next guess.
Mm-hmm. Usually one is all. If it takes more than that, you probably guessed wrong in the first place and should start over. Anyway, so that's the basics of running this. Now, let's try something that's a little more difficult. This is a linear example. I'm trying to do a third order fit to a surface. So I've got a surface, it's a curved surface, and I want to do a third order fit. And you think, well, it doesn't sound too bad, except the SVD solution has massive round-off errors, and it fails to find a good solution. So there are two things you need to do. One is what I term scaling parameters. I've seen it called other things other places. I think the fitting routine in Excel does it automatically for you, but I'm not positive. Basically, the problem is that the parameters for this fit, well, actually, why don't I just show you? That would be much easier. Okay, my apologies. I wrote this VI on a much bigger screen, but it shouldn't matter too much. Okay, so basically what I've got is I've got a XY grid of data points. Okay, the X and Y's are at certain points, and then I have a pair of what I'm calling X and Y for reasons I can't say, which Z values. Okay, so I've got X and Y Z values, and then I've got an XY grid. So when I click the button here, this is what the X data looks like. This is what the Y data looks like. When I run an SVD fit on it, these are the parameters I get so it's constant X, Y, X squared, Y, etc. X times Y, X squared, Y squared, x squared y, y squared x, etc., all the way to the bottom. And you can see that the SVD fit, the function doesn't fit very well. The range is horribly off, and the corner values, which you can see from the result I got using the downhill simplex fit, are off by 6 orders of magnitude. But if you look at it, you will notice that there are something like 24 orders of magnitude between the different coefficients here. And that is way outside the 15 to 16 orders of magnitude you get in a double. So as a result, when you use the SVD on this, it sees this 525749 and just starts rounding things down to low numbers, which as low as it can get is like 10 to the 12, 10 to the minus 12. Because relative to the other numbers, that's the difference. So what you do is before you call the downhill simplex, you scale the values so that it's operating on things that are all more or less 1. So, and that's what that auto scale. Yeah, that's not what I wanted. So let's go back to that generic error function and actually it's not the generic error function I want. The minimizers, generic minimizer, and the find minimum. If we go back to this auto scale here, if there are a couple of values that I can set that use scaling. Now I have the choice. I can either set it myself or I can use auto scaling. And auto scaling, all it does is it takes the log of the number, finds the order of magnitude, scales it, records the scaling, and puts the change numbers back in as the initial. And then when it actually does the fit itself, it passes at the scale numbers. But the values, the parameters that the fitting routine is using are all numbers close to 1. The values that the function is evaluating are going to be the actual values. And as you can see, that makes all the difference in the world. Because this and this are virtually identical, so the function works quite well. I've got fairly randomly scattered errors here. So let me dive into code. So what I've got is, like I said, an array of a 5x5 array of z values. I've got 2 of them. They're actually independent, so it doesn't really matter. And then this is generating the XY grid of points. And this is actually one of the reasons there is a problem, because the points are separated by 67,000. And when you start squaring and cubing that, it gets really big really fast. So I don't want to get into this because this is raw, low end, very low level code for generating an SVD on a 2-dimensional array. The SVD code included with LabVIEW only works on single dimensional arrays. So I had to modify it and pull it apart and do this. So this generates the SVD fit. And the rest of it is basically the same thing except for this VI, which turns on the scaling and turns on auto scaling. And there are 2 copies here, one for the, you can see one for this is for the Y. Set the parameters, find the fit, do it again, find the other fit, and that's it. I cheated here and used once I created the minimizer, I just used it again here with a different set of initial values because I had it all set up.
Damien, if you have been to MATLAB or any other program that will normally, how much more work would it be?
I don't know because I haven't done it in MATLAB. I have tried it. I've been playing around with SageMath lately because I've been doing a lot of optics calculations and I didn't see a lot of this level of detail in it. I would probably end up having to do the parameter scaling myself beforehand, and basically kind of go behind the scenes and use, for Sage Math, I know I'd probably have to use global variables to pass the scaling factors into the functions, and then to kind of trick the fitting functions. It's doable, but
So one of the things that I've seen when I work with people who have PhDs, and I tell them, you just tell me why you won't code it, and I'll make it happen. Don't expect me to understand what you're doing. That's why I said I kind of know about data. I think it's the chip registers, the thing that the uninitialized chip registers is something that makes it a lot easier to do those crazy math stuff. And in general, the visualization of the graph needs to be what they find. But yeah, I just was curious if there was why would you choose to do it with LabVIEW instead of doing it with something else?
I'm doing it in LabVIEW because I need to run fits on a SB Rio at a kilohertz. I had no choice. It had to be LabVIEW because that's what the code is. And the existing LabVIEW code didn't do it for me. And I also, one of the main reasons I went to the object-based approach is I wanted to be able to try multiple fitting methods rapidly. I wanted to be able to change the fitting function rapidly. And using the object-based approach, it was very easy to do that. Using the existing LabVIEW code, it would work. Actually, it didn't work because I couldn't do my function in the equation parser thing. It just didn't exist.
So are you planning on sharing some of this, or?
Well, I can certainly. Yeah, there's nothing in here that I can't share. So I was planning on giving you a zip file of everything and the presentation.
Yeah, if you want, I can package it. So it's a VIPN package.
Okay. Yeah. Well, it's just a copy. Yeah.
Yeah, well, the thing is that then it will become part of the palette.
Yeah, the biggest issue with this is I wrote it in LabVIEW 2016, so I'll have to back save it. How far back do you want it?
Well, I'll save it as a package. If anybody wants something younger than that, they can hire you.
Pretty much.
Anyway, but that's basically all I had to show. Future things, I did find myself playing around with the distribution type, whether it was Gaussian or Lorentzian, whatever, quite a bit. And I was tempted to move that from the actual function where on a lot of my functions, I actually had a diagram disable, and I had either an x squared or an absolute value or a log of 1 plus the absolute value in that, and I would just switch it depending on what I felt like doing. The main reason I did that was for speed, because I'm running on a fairly slow processor. It's a 9027 SB Rio. So it's 800 megahertz ARM. It's not lightning fast. And the killer for all of the bottleneck for all of these things is the execution of that function, because that is what gets done over and over and over and over again. You could probably make it even faster by not making it class-based and just have something else. But because that way you avoid the dynamic dispatch of the overhead. But
Well,
if I remember correctly, that's almost non-existent once you've done it the first time, unless you actually change.
well, then dynamic dispatch call is single-digit microseconds, which can matter, but it's going to be faster than a lot of your other methods. So if you've got a function swap, you've got a function swap, and you're not going to. I think.
Single memory copy will be worse than the overhead you can find.
Yes, I know.
It's like the other things you
Yes.
Your VI server calls are going to.
Well, that was another thing I did when I did these, is I cleaned up the fitting regimes quite a bit. I did not clean up the conjugate gradient much. There is a VI in there that is genuinely scary. It's got, I think, 20 local variables, and and you can just look at the thing and see race conditions all over the place.
Yeah.
I did not have the guts to dive into that. It would have taken me probably 4 or 5 hours to fix it, and it wasn't worth it. So, if someone wants to do that for me, yeah. Because conjugate gradient is usually much faster than the downhill simplex. But as I said, it's not quite as robust. So.
We have the fastest FD so that's good.
Yes, I do.
On the back-end implementation, I guess for some of those math functions, did you look at potentially using like math scripts as opposed to a lower-level math function? Or is...
I did not have a math script license at the time. I do now, but I didn't then.
Those will not be faster. Depending on the call. Those will not be faster.
I did.
They will not be faster.
I did find well, when I was.
Do we have a little years for next meeting to talk about?
I want to see the benchmark.
Yeah, I want to see benchmark.
Well, I did notice that there was. I always assumed that the standard LabVIEW math functions were fast and efficient. That is not true. Even if they're calling a DLL or whatever, they're not necessarily faster. I was calling a standard LabVIEW math function that, and I found out that was my performance bottleneck. And when I rewrote it using a standard algorithm from Wikipedia, I got a 10x in performance improvement.
You know, one that has in a lot of my customers, all that math functions I use point by point.
Yeah, this was not a point by point.
No, but I'm
Yeah.
just going there because that's another one. That's why I was asking you.
Yes.
Because they worked great on their proof of concept for a single set of data sets. And then they start putting it in portals and calling that same function in different areas of their code.
Yeah.
And they started discovering, crazy black holes and stuff that they were not expecting. And it's because the point by point actually is an accumulator. It's like a function of all variables.
Yeah.
And you're calling all the different areas of your code. I don't think it's well documented. I think
There was a problem where it was marked as a non-reentrant BI at some point in the past version, but it should be reentrant.
And then go drop those guys into a dynamic dispatch call, which is shared.
Well, that's just
yes.
You'll be talking about your conjugal business there.
Yes, yes.
Because the problem is if you have it inside a for loop, for example, or while loop, and you're getting all your arrays in it, the developer that is coding it thinks that each input is getting its own accumulator, but it's not. They're sharing the accumulator.
Currently it says pre-allocated costs, so they should all get pre-allocated. In the for loop.
And then drop it into a shared clone VI.
If you drop it,
Do it, it's fine.
Just drop the cameo buffers, absolutely.
Oh, yes.
But it'll have a good time.
Anyway.
You'll hate yourself in the morning.
I already went through one of those this week. I added a simple. I added a simple Q reference to a class, and one of its class members didn't update its front panel variable. So when it downloaded it to the FPGA, or to the Rio, it corrupted the heap and wouldn't download. It was not shown as broken or anything. And I did a force recompile of the entire thing, and it didn't fix it. I ended up having to, when I finally figured out, I ended up having to delete the two class front panel objects, drag them back on, reconnect it, everything's fine.
Did you, out of curiosity, also try clearing the compiled object cache?
I was going to, but didn't.
Okay.
Actually, no, I did. Well, the force recompile should have done that anyway. No. I'm talking about the LabVIEW force recompile. I'm talking about one I wrote that goes through VI by VI and does a force recompile on everything.
Not the compilation, it's the deployment process to the Rio and how it checks whether or not things have to be deployed or if they're already there and that.
Oh, I restarted the SB Rio. In fact, I actually wiped the disk and restarted it. Because I had been doing a lot of downloads to it and had startup stuff on it and things, and it was in a weird state and I didn't want it there, so I just wiped the disk totally, reformatted it, put a new software on it. Didn't matter.
Dr. Gray firmly believes in dusting off and nuking the site from orbit. It's the only way.
No, it's not. All I really needed to do was replace those two references on the front panel. Anyway, any other questions?
Thank you.
Okay.
Always nice to see it. Always nice to see LabVIEW applications with a little class.
And numerical methods.
Well, most people in LabVIEW when they think about classes, they're thinking about how. They're not thinking about their operators necessarily.
Yeah, most classes I think will start with how.
Yeah. And then they're,